graphs for n. Okay? So anyways, that's the basic idea of space-time diagrams, and we will talk a lot more about this as we go along, and we will actually figure out exactly this time dilation, etc., etc. Okay. So, what I want to do, just to get some practice with drawing space-time diagrams, and also to introduce some very important concepts which will be useful when we try to understand the true nature of time. I want to consider a really, really simple situation experiment. Okay, this is a sound in air experiment. Okay, so the idea is something like this. Here's our experiment. Okay, so we've got Alice here. Alice is at rest. Okay, so we're going to draw the situation first in space. By the way, experiments in special general relativity tend to be extremely simple. Essentially very deep. Okay, so here we go. So here's Alice's x-axis, and she is at rest. She's just standing here at rest like this. Okay, and what she does is she claps her hands, and what happens is a sound wave moves radially outwards in all directions, and this sphere expands at the speed c in all directions. In particular, we will be interested in 2 points on that wavefront that's moving outwards. Okay, one of them is the point on the wavefront here that's moving to the right, and the other is the point on the wavefront here that's moving to the left. So we're interested in this point on the wavefront, which starts right at her hands and moves to the right at the speed of sound from the air. So you're imagining that Alice is at rest with respect to the air. She claps her hands. This wave goes out in all directions. We're interested in the part of the wave that's going to the right and the part of the wave that's going to the left. Okay, so the part of the wave that goes to the right goes to the right of speed c. This is the speed of sound relative to still air. Okay, and we'll look at this part of the wavefront, which is moving to the left. This point over here on this wavefront starts at Alice's location and moves to the right at a speed c. So what is its world line in Alice's space-time? How do I draw the world line of that point on the wavefront as it moves from her location to the right? Yeah. Yeah. Okay. So it's going to be some line that has some slope here. Okay. If the speed of sound is very small, that means it will cover. It will take a long time to cover a small distance. And so the world line of a slowly moving sound wave will look like this. Okay, if the sound wave is moving very, very quickly, that means it covers a great distance in a small amount of time, and the world line will look something like this. Okay, so it's important just to get into your head that world lines that are vertical are at rest with respect to Alice. World lines, as you tip the world line more and more and more, you're representing something moving faster and faster and faster with respect to Alice. This is 0 speed, this is infinite speed. Okay, the speed of sound is moving at some speed between 0 and infinite, some finite speed, 500 meters per second or something like that. Okay? Now there's a very, very convenient trick in order to make the world line of a sound wave exactly at 45 degrees. It's somewhere between here and here. It's convenient to choose basically the scale of this axis such that it's at 45 degrees. Okay? So how do we do that? Well, the way we do that is very simple. Instead of plotting time versus space, instead of plotting t versus s, what we plot is c times t versus s, where c is the speed of sound. So how does that help us? Well, let's see. Suppose that the sound wave, we're watching the progress of the sound wave, and it's moving through Alice's space. And suppose that at some time it has covered a distance d. Okay, so it has gone out to a distance d. So in this picture, as time has gone on, the sound wave has moved to the right, and it's moved out, say, to a distance d. Okay, in other words, we're sitting right there. Okay, so what is the corresponding time? How much time has elapsed for Alice? Here, actually c times time. Well, we can figure this out. The time that has elapsed for Alice, time is just distance over velocity. So what is that? d over c. So what is c times t? Remember, we're plotting not t versus s, but c times t versus s. What is c times Alice's time? Just d. Okay? So that means that's just d. So if that's d and that's d, well then this must be 45 degrees. Okay? So very, very convenient to plot ct versus s instead of t versus s. What about this wavefront? What is its world line in this picture? Diagonal the other way. Okay, so as time goes on, the other wavefront moves to the left. Okay, so diagonal the other way. If I'm choosing to plot ct versus s instead of t versus s, it's also 45 degrees. Okay, so that's that. One thing to point out here that's very, very important is what are the units? What are the units of c times t? Meters. Okay, so, or just a distance. Okay, if I take a velocity times the time, that gives me a distance. If I'm using meters to measure distance, that is meters. Okay, so CTA, that has the dimensions of length. Okay, what are the dimensions of SA? Same. Okay, so both CTA and SA have the same dimensions. say meters or kilometers or light years or whatever. You can measure them in the units of meters. Okay. So, in other words, what we've done is we've changed our space-time diagram from, say, seconds on this axis to meters on this axis to meters and to meters. We're plotting meters versus meters. We put space and time on the same footing. It's very important. Okay, we put them on the same footing because eventually what we want to get to is the fact that space and time are not separate entities, but they are in fact parts of, just two different parts of a whole. Space-time. Okay, so in Einstein's picture of the world, space and time are unified together. They're welded together into this structure called space-time. So for Newton, space was absolute and time was absolute. For Einstein, neither space nor time are absolute. They're both relative. And what is absolute is space-time, at least in special relativity. And in general relativity, this space-time itself becomes not absolute. Okay, but anyways, so we will talk about that as we go on. But the point is, by plotting CT versus X, we're now treating space and time on the same footing. Okay? Right. Okay, next. Let's talk about a certain thought experiment. So you may know that Einstein was famous for doing these fantastic thought experiments, which led him to all kinds of amazing insights. We're going to do a very, very important thought experiment here, which is initially going to tell us a little bit about the Doppler shift for sound moving in air, but ultimately it's going to tell us about the true nature of time. Okay, so it's a very important thought experiment. Okay, it's going to be very, very simple to begin with, but then it's going to get conceptually very deep. Okay, so here's the experiment. So what we're going to do is, we're going to start down here. Okay, so this is Alice's space axis, SA. Okay, and Alice is down here, and Alice is at rest in her space. Okay, so her world line is just a vertical line, so let's put we're always converting a space diagram into a space-time diagram. Okay, so Alice's world line just goes up like this. Okay, so we got that. And remember, we're not putting TA here, we're putting C. Time according to Alice times the speed of sound. Okay, and Alice is at rest with respect to the air. Okay, now we're enter another character, Bob. Okay, so Alice is going to be standing here at rest in her space and at rest with respect to the still air. And Bob is doing something very simple. He's just drifting by her like this at a constant velocity. Okay, so in a space diagram, we would have him walking like this with some velocity, V. Okay, so that's Bob. Now, let's suppose that Alice's clock reads, say, 0 here, or this marks the point at which Bob crosses Alice's path now. Okay, so at that point, so prior to that point, Bob was to the left of Alice. After that point, he's to the right of Alice. Okay, so this world line will look like what? Okay, let's diagonal to the right. Let's tilt it a bit to the right. Okay, but not too far. Okay, I can add to this diagram something. So something is moving at subsonic speed. Here's an example of subsonic. Okay, the tilt of the world line from the vertical is less than 45 degrees. Here's something moving supersonic. The tilt of this world line is greater. We're covering more distance in the same amount of time, and we're moving faster than the speed of sound. Okay, so we're going to see that Bob is moving at less than his velocity v is less than the speed of sound, so he's subsonic. So his world line will be tilted at less than 45 degrees. Okay, so we got that, and this is Bob's axis. So as Alice's clock ticks, there are tick marks on here: 1 second, 2 seconds, 3 seconds, 4 seconds, so on. As Bob's clock ticks, that's 1 second, 2 seconds, 3 seconds, so on. Okay, so we've got that. The next thing is, what we're going to do is, we're going to imagine this situation. So Alice is at rest there. Bob is drifting by like this. Okay? The instant that they cross paths, they both zero their clocks. They hit 0 on their stopwatches. Bob continues drifting like this. Okay? And then at some point, he's just drifting like this. Okay, now from Alice's point of view, what she does is, after Bob crosses her path, she looks at her watch and she waits a certain amount of time. Say T. Say capital T. So it's another sign, capital T, on her watch. And then she claps her hands like this, which sends a sound signal chasing after Bob. Because Bob is moving at less than the speed of sound, that sound signal will eventually catch up to Bob and hit Bob. And Bob will hear that sound signal. Okay, and as soon as he hears that sound signal, what he does is he claps his hand and he sends a sound signal racing back towards Alice. Okay, so that's the experiment. Okay, so the first thing is, from the time that Bob crosses her path, she lets Bob drift to the right for a certain amount of time, say capital T on her watch. Okay, so what is, where do I put that point on the CT axis? So let's say here. Okay, because we're plotting C times T, we plot, well, C times T. Okay, so at this point over here, Alice sends a sound signal. She claps her hands and sends a sound signal chasing after Bob. Okay, so how do I draw that sound signal chasing after Bob? 45. Okay, so this guy's going at 45 degrees like this, and it is Bob over here, so that's 45. Okay, okay, so, and now, that sound signal chases after Bob and eventually reaches Bob, hits Bob, and then Bob sends a sound signal back to Alice. Now this is an extremely important point, so we're going to spend a little bit of time on this. So Bob is drifting like this, okay? he hears the sound signal, say, at this point, and then while he's in motion, he goes 10, and he claps his hands and he sends the sound signal chasing back toward Alice there. The question is, with what speed does Alice reckon that sound wave is coming at her? Yeah. Okay. Any other ideas? So you're on the right track. Because he's in motion to the right like this, when he claps his hands like this, it's not totally, maybe not totally obvious what the speed is going to be, or what speed Alice is going to measure. Okay, so maybe it's the speed c minus d. Any other ideas? The same speed as the c. Okay, so how many say it's just c? How many say it's c minus d? How many don't know? That's not good, okay. So the fact is, the speed is just c. Okay, and it's a very, very important point. So let me just write this down, and then we'll talk a bit about this. Okay, so I want to make a statement here. Actually, I'll get rid of it here. Fact to do with sound in air. Okay, so what's being said here? Yeah. So with respect to, let me read this out. For observers at rest with respect to the air, the speed of sound that they measure is independent of the motion of the source of that sound. Okay, so the statement is that although Bob is in motion, here he is drifting relative to Alice and relative to the air. When he clasps his hands, the sound, the wave that he emits in all directions, the speed of that sound will be measured to be c for someone at rest with respect to the air. The reason for that is that sound is a vibration of air. Okay, so when I'm at rest here and I clap my hands, what am I doing? Well, basically, I'm sending out a whole bunch of air molecules, okay, and those air molecules bump into the neighboring molecules and cause them to jiggle, and those then in turn bump into the neighboring molecules, cause them to jiggle, and so on. So it's like a domino effect. So when I go like this, I'm causing a domino effect of air molecule vibration going out in all directions. Okay, and that air, those vibrations move with the speed c the same in all directions. If I'm a moving source, if I'm walking like this, and I clap my hands like this, just like I clap my hands, I set up some disturbance in the air. Okay, now I might move on like this, and my hand might be going up here, and I'm clapping like this. I'm a source in motion. But as soon as I set up a disturbance like this, then that disturbance takes on a life of its own, okay? And it moves, it expands in a sphere centered at the point of the disturbance. Okay, so let me show you a little atlas here, which might make this a little bit clearer there. Showing you the Doppler effect. So we know what the Doppler effect is. What's the Doppler effect?
It's kind of like how the sound is like it's from the source, but no matter how far close it is, it's totally different. I don't know.
Okay. How far or closer do you mean how motion? Do you mean how fast or slow?
Yeah, how fast or slow is going.
Okay. So if something is moving toward you, then the frequency of sound is on the
floor. It's like close together. Okay, so it's more high pitch sound.
Right. So the classic example is an ambulance. So here is an ambulance. So this ambulance is showing you an ambulance just moving along here. And that ambulance is emitting sound waves. Okay, so it's like the ambulance is passing the moving source of sound. Notice that each time the ambulance emits the sound wave, it creates a disturbance in air, say, at that location. Now that location, as soon as it creates that disturbance, that sound wave moves radially outwards in all directions, centered on that location. Okay, so there's a sound wave emitted, there's a sound wave emitted, there's a sound wave emitted. And once it sets up a disturbance in the air, then that wave moves with respect to the air. Okay? So there are two things going on here. One of them is this Doppler shift. Okay, so you'll notice that here's our observer, and here's the sound waves coming forward our observer, and the wave fronts are closer together on this side. So the wave fronts are washing over our observer more quickly, they're coming fast. So when the ambulance is approaching, we have an increase in the frequency of sound of the ambulance. When the ambulance is receding, you'll notice that the distance between those wave fronts is now greater, and the wave fronts wash over our observer at a lower frequency. Okay, so when the ambulance is approaching, the pitch is higher. When the ambulance is receding, then the pitch is higher and lower. Okay, so that's definitely an effect. Okay, so the Doppler effect is definitely there, and we're going to try to calculate that. But what I'm trying to focus on here is the fact that the speed of this wave here, as it approaches the observer, whether the ambulance is approaching the observer or receding from the observer, the speed of these sound waves in any direction is the same as what we see relative to an observer at rest with respect to the air. Okay, so that's a very, very important concept to have in your mind. So I think that makes sense. Does that make sense? Are you okay with that? Yeah. That's right. So no matter what the source is, if I have reference respect to the media, and you've got a timer, and you're running around the room doing this, moving away, moving forward, and so on, I look at all kinds of doctors and stuff. You're running forward, single timer, you're running away, and so on. But if I were to measure and see that sound, once it's created, moves like a domino effect relative to still air. And so the speed of that wave is always c in any direction. Yes. What about the speed relative to the light motion? What would be the speed of sound? Will it be the same thing or a little bit decrease? The speed of sound for it's something distortion. Yeah. But then it'll change. So if you're say a source at rest, you're a timer at rest, I will measure some speed, right? If you're moving forward or away, it doesn't matter, I'll measure the same speed. But now if I start moving relative to the air, well, that's a whole different story. Now say you're a source at rest, you're sending sound waves to me, they're moving with the speed c relative to the sound, as well as relative to the air. If I'm now moving relative to the air, towards you, I'll measure much speed. Okay, so it's very important if you're all this stuff applies when you're at rest with respect to the air. Yes.
So there you said that if it was like a vertical line, it was like 0, and I said increase in velocity across like infinity at the x. What does that mean? Like speed at the x and then like the final path once you get like
So you're jumping the gun here. So yes, it is true that when something is moving at the speed of light, if something is massive, it can move at the speed of light. In which case, yeah, basically the time dilation effect becomes extreme. And there's no time elapses. So if you're a photon moving across the room, it takes you no time to get from there to there. No time elapses. In fact, if you can travel across the entire universe in no time. So we'll talk about that later. In this picture, all we're thinking about is sound in the air. Because that concept there first. Okay, so we said all that. When Bob claps his hand right here, he's a moving source. He's drifting out like this. He claps his hand and sends his signal back to Alice. With what speed does Alice make that sound wave coming out of it? At what angle by law does this sound come out? Okay, that's super important. This angle here is really important. Okay, so we got that. And what else can we do with this diagram? Well, we're going to add a few more details to this diagram. In fact, we're going to add the distances and velocities on the sound. So Bob is moving with some velocity to the right. Okay, now let's suppose that when Bob receives that sound signal, he has covered a certain distance d in Elliott space. Okay, so he receives the sound signal when he has traveled a distance d. So that's a d sitting there. Okay, so if this distance is d, and that's 45 degrees, what is this distance? Okay, this is also d. It's not your favorite, is it? That's very important. Okay? That's how convenient this is. Because we're measuring x, and we're measuring space and time both in meters, like c times t. This is in meters, that's in meters. Okay, so if that's d and that's 45 degrees, that's d also. Okay, d meters. What about this guy over here? Also d. Okay, so we got that. And what else can we add to this diagram? Well, let's find the expression for yeah.
So a little bit of like time pass between the return class. Like, would it not form a perfect triangle like that?
Because of the time that it takes off the process? Yeah, so we're going to find. So in other words, another way to think about that is Alice pushing her hand like this, sends the sound wave here, and Bob has a big one here. So there's no thinking about it at all. Or we think Bob is just working the finger. Okay, so there's no time left. Alright, so we got that. So let's talk a little bit about the relation between this distance and this velocity. Okay, so we know that distance d is velocity times time. So what am I going to put for velocity? D. What am I going to put for time? Think about this. Look at this picture. Well, it started at Alice's location. By the time you receive that sound signal, he has traveled the distance d. How much time has elapsed for Alice? How much time does this... So Alice reckons that Bob receives that sound signal when he is located a distance d from her, and a certain amount of time has elapsed for her. How much time? Yes. So it's this time over here. So Bob crossed her path, and he moved the distance d. How much time did it take? Well, this whole time. Okay, so it's ct plus d. Okay. But that's c times the time. I need to divide by c to get the time. So we've got that. So here in this formula here, there's a d there, there's a d there. And what you can do is you can solve for d, and I'll leave that as an exercise for you to do. So, in fact, what we want to solve for is the ratio of d divided by c. And so we can get is d over c divided by 1 minus d over c. Okay, so I won't go through that simple algebra. You can do it later on tonight if you want. This is a very important equation which we'll use many times. Okay, this we'll call equation number 1. All right. And finally, we get to the really important part of this figure, and that is how much time elapses for Bob from the time he passes Alice's location to the time that he receives the clap. Okay, remember, Bob is drifting across Alice's frame. As soon as he drifting past Alice in her space, as soon as he passes Alice's location, he zeroes his clock. Time is ticking for Bob. Tick, 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 tick. That sound wave comes, hits him, boom, and then how much time do you have to Bob's clock? So according to this diagram, how much time is that? Here.